So I'm really happy to be here to talk about the work that I did with my colleagues at WayUp over the last, call it, year and a half. Sort of two notes. So first of all, if you didn't catch the tense, I actually left WayUp a week ago and have started on Monday at Teachers Pay Teachers here in New York. But I'm really, proud of what my coworkers and I at WayUp have been able to accomplish over that time with a very small team. So I'm really thrilled to be able to talk with you about that today. As Robert said, I was the only full-time data scientist. I wore a data engineering hat as well, as I'll mention briefly. But the work that I'm talking about wouldn't be possible without my colleagues on the engineering team who helped me build this system, get it into production. All right, so what I want to talk about today is how some of the constraints from the business and the way that we've built the site, as well as the scale of the team, very small, led to a bunch of decisions that we made around algorithms, software architecture, tools, as well as just in what order did we tackle different things. And that's kind of going to be the theme throughout the talk today. So to ground you a little bit about WayUp, WayUp is the leading platform for connecting college students and young professionals to entry-level jobs, internships, and part-time jobs. And it's important to know something about the business model here. So WayUp is a company that gets its revenue from companies that are looking for talent, so posting jobs on our job board. In the case of some of the larger companies, also getting other types of employment branding solutions, things like social media, blog posts, and so forth. So one of the challenges, if you are maybe a large old company, is trying to convince 21-year-olds that maybe have never heard of you that they really want to go work for Unilever, which is a really good company to work for. So a lot of it is trying to sort of to promote these companies to people who might not otherwise be aware of them or be aware of those opportunities. So in terms of the technology, we have this job board, a mix of jobs from WayUp customers as well as jobs from other distributor sources maybe feeds that you've heard of. And one of the other components of the system is sourcing. So when you sign up on WayUp as a candidate, as a user, you have a profile. It's like a really kind of millennial-friendly, on-brand version of maybe your LinkedIn profile, kind of a similar idea. And like LinkedIn, you get messages from employers who look at your profile and say, oh, hey, you should consider applying to our jobs. So from the point of view of a user, you're 21 years old, you're just graduating from college, you run across some branded content on Instagram or something like that, make your way to wayup.com, and what we do is we have you fill out a profile using what we call Mad Libs here approach to get a lot of information about you. So we know your major or majors, we know where you went to college, we know about your job history, we know all sorts of things, and all of this happens in the first step, again, to make it valuable for employers to do this sourcing step as well. So after you've filled out your profile, then you can come to the main jobs listing page, start browsing jobs, applying for them. In many cases, it's as simple as clicking on an apply button to send your profile to these companies. And so, okay, kind of the first question is, recommender systems are a fair amount of fiddly technology. Why would you want to build one of these things in the first place? And there are a couple of really good reasons. So first of all, you guys, me, when we're looking for jobs, not that hard. I basically type in the title I had for my previous job, and I find lots of jobs that have the same title. If you're just coming out of college, if you're looking for an internship, you may have no idea what's out there. And so in that case, it really is beneficial to the users to, hey, find some suggestions that might be non-obvious and make sure that people are seeing those. Additionally, like I just said, you just spent 5 minutes filling out your profile. You told us about what you've done in the past. You've told us fun facts. You've told us kind of your major. You really want to have a great experience. This isn't like Netflix, which we just heard about, where it's fine if you get a mix of romantic comedies and samurai movies at the beginning because you don't expect Netflix to know anything about you. But for WayUp or a company like this, where you've told us a great deal, you do have those expectations, and we should try to meet them. And of course, WayUp is a business, and it would behoove us to promote customer jobs, maybe a little bit on top of other jobs from distributors that you should be applying to as well. And so for all these reasons, it makes sense to have a recommender system, not just be like Indeed.com with the search box. Okay? So on top of those business constraints and site design constraints, we also have scale constraints. Here, not developer scale, but actually technology scale. So at any given point in time, WayUp has about 100,000 job listings that are available for it to recommend. And after you've finished filling out all those Mad Lib steps to generate your profile, we've got on the order of like a second to come up with recommendations. So this is not a batch job that's running overnight to do collaborative filtering or anything like that. We actually have to do this generation, this matching to recommend jobs really, really fast. So we can't leverage very slow processing. We can't do anything that requires interaction history. So any type thing like collaborative filtering, item recommendations, you haven't looked at any jobs yet. We have to do something different. And we also can't do anything that takes a lot of time over those 100,000 listings. We have something like 10 microseconds per listing, which, computers are fast, but still that's not a ton of time to do something in real time. So a lot of the technology decisions are based on this constraint as well. And so, yeah, that's all these together it's a fairly hard problem to do well. And I don't want to claim that we're doing super well, but definitely made some good progress. So again, constraints so far. The business model means we want to put the thumb on the scale a little bit. We want to include any heuristics that we have about what jobs might be appropriate to you based on all the data that we have, any metadata about the jobs themselves. The profile before browsing means we have to base the recommendations on who you are, not what you've done. And we have this real-time component. We have to think about efficient algorithms. And like I said, limited resources, 80-20 solutions are great. Anything that gets stuff in front of users is great, and we don't have a giant team to invent new wheels or anything like that. So the first decision is, okay, I came in 2017, what do we want to do first? So there was a recommender system that was in production. It had been built by mostly software engineers. And really what it was enhancements to the search system that used a whole lot of business logic based on the user's profile to come up with a plausible set of jobs that you might be interested in. Didn't really have machine learning. It really wasn't great for a lot of users. It was impossible to iterate on. It was so tied to the details of the implementation. But it wasn't so bad that it needed to be replaced immediately. So we did some other things first. So the first thing that we really worked on was trying to improve data quality. So this obviously is a data engineering conference. I picked up a data engineer hat and worked with our business analysts to build a data warehouse to give a much cleaner data source for pulling historical information, for pulling information about jobs, for pulling information about users, interactions, all that together in a much, much cleaner system. Happy to tell you about that later. Also spent a bunch of time working on metrics. So when I came in, there was a system, but there was absolutely no way to measure how well it was working. So we put in a bunch of features to greatly improve that system. Things like taking snapshots when you apply to a job. It'd be really nice to know where that job was in the hypothetical recommendations list, even if you came across it a different way, like search or an email message with an invitation from a business user, something like that. Started calculating metrics, technical metrics, things like the mean minimum log rank, which is sort of a variant of a standard recommender system metric. Basically, that says, how close to the top of the rankings are the things that you applied to overall. We also use some more business-friendly metrics. I like this sort of basically precision type of thing. What percent of users applied to one or more of their top 10 jobs over a period of time? This is very easy to communicate, unlike that previous one. We set up an A/B testing framework, so allowed, based on user ID, different people to see different variants of the existing system that initially had a bunch of free parameters that we could tweak, and the same system is in use with the new recommender as well. So once these sort of foundational pieces were in place, it made sense to, given everything we've learned, given that technology, to put everything else aside and start over with a from-scratch implementation of a new recommendation system. Okay? So I'm going to tell you a fair amount, primarily about the architecture, to some extent about the algorithms that we've put into place. I'm going to start out with the real-time piece. So that what happens when, after filling out your profile, you come to the jobs listing page for the first time and get a set of jobs in a feed. So kind of after deciding to go ahead, the next decision is, what is the architecture? So the old architecture was this sort of monolith where the data scientists who might want to try new algorithms are going to be working within the main application framework. And it, again, was very tightly tied to the existing Elasticsearch implementation, which really strongly restricted what was possible. So the decision was to go ahead and totally separate, build a new microservice, build everything else from scratch, and this has worked out pretty well. So to kind of walk you through what's going on here, you come to this page, and essentially what you're telling your web browser is like, hey, I'd like to see some jobs now. You have a user ID, you might have some other types of information that you're kind of about your user. That goes to the main application and says, great, that's pretty hard though. I don't really know how to do that, but I do know who you are. So it grabs your user profile information from the database. This is obviously where this is stored, the main applications database, constructs a profile, sends that to this microservice that says, okay, I know how to do this. I can apply all of the feature engineering, all of the domain knowledge that data scientists have about how to take this profile, turn it into something useful. That's where this happens. The microservice has its own data sort that has been previously set up by an offline batch system, sends back a list of ranked listing IDs to the main application. The main application then pulls up everything that the UI needs to actually display those. So things like the logo and what have the UX people decided to go on the screen, pulls all that information and sends that to the front end for display. So why did we do this? This was a fair amount of new code, and the main reason is one of my favorite things to harp on, which is separation of concerns. So this is a software architecture term, meaning that each subsystem should be specialized, and subsystems shouldn't need to know about the internals of other subsystems in order to do their job. So in this case, this means that the main application was built by software engineers using their tools, and data scientists don't really need to know what's going on. The main app obviously knows about users, and all it has to do is it speaks its own languages, things like JSON objects, pulls fields from the database, sticks them directly in this object, sends it over the wire, doesn't need to know about feature engineering, doesn't need to know about algorithms. The recommender service, on the other hand, is built, tested, and deployed by data science, machine learning engineer types of persons, and what it knows about, in general, is job listings. It knows what to do with users, but it doesn't store that information. The recommender system then, like I said, parses that profile object, does feature engineering, and runs the recommender algorithms. In addition to then returning that to the main app for display, the recommender microservice is very scalable in that it's basically doing this one simple task. You can run a bunch of copies of it. There's no sort of stored information that needs to be kept in sync. This is great for dealing with like peak periods or like when you have to send recommendations to 1 million people by email. So that's the high level sort of software architecture. I want to talk a little bit about the algorithmic level, particularly kind of in the ways that apply to those constraints that I started out. So it's pretty common in industry situations where you're having to do this real-time recommendation framework and you have a lot of things to recommend. If you only have 1,000 things to recommend, computers are pretty fast. But when you start having 100,000, a million, or more types of things to recommend, it's very common to have kind of a two-step process where you do a very fast, quick, rough algorithm to get you, in our case, down from like 100,000 to maybe 1,000 or 100, using whatever you got, heuristics, some sort of learning that can be scored really quickly, and then you can use whatever tricks you've got up your sleeve to re-rank the top 100. So maybe the thing that was originally ranked 37 would be the thing that the user is most likely to click on and apply to. You would really like to use whatever fancy algorithms you've got to make that possible. And so that's the pattern that we put into place. So let me kind of walk you through what happens inside the recommender when it receives this JSON blob with the profile of a user. So the first thing, and there's a bunch of arrows, I'm going to do my best to kind of walk through this. So the first thing that happens is what we call a rough ranker applies. So this is a very fast, not very precise ranking system. I'll talk a little bit about the algorithm here in just a moment and explain how and why it's fast. One of the things that it does is it takes the jobs that you have previously interacted with or applied to and finds other jobs that are similar using sort of this secondary similarity algorithm, which I'm not going to go into detail on. All those things together come up with this listing of, let's say, 1,000 jobs that you might be interested in some sort of rough order. Some of these, which I've highlighted in yellow, are WayUp customer jobs. Some of them come from other sources. And then you want to take the top, let's say, 100 of them and re-rank them. In this case, 100 is 3. I've just redefined it for today. And so you've got the original rough ranking. You've got this Finery Ranker, which I'll talk briefly about in a minute. And then we also, and so maybe that one decides that number 12 is better than number 17 and puts it at the top. And then we also have a thumb on the scale piece, which literally just says, if you're a WayUp job, that's a WayUp customer job, that's better than being a distributor job. It puts those to the top. Then a pretty simple merging algorithm uses a kind of a weighted approach to combine everything and grabs the rest, 101 to 1,000, grabs the rest of those listings, puts everything in an object and sends it back to the main application. We've got a smart Finery Ranker and a really stupid but smart from a business perspective WayUp customer job booster as well. Make sense? So how do we do this kind of rough ranking thing? The intuition here is that you can get pretty close in a lot of cases just by using tags. So users, you can take that profile, turn it into a big list of tags. Listings, you can grab metadata, you can grab text, generate a whole bunch of tags. And to the extent that they overlap, that's pretty close to matching. Now, of course, we do a bunch of heuristics, business logic to try and get this to work as good as possible. And so you end up with tags like internship. And so an internship might be a tag that is a property of a listing, and you also know something about, hey, this user is still in school, so probably might be interested in internships. You create a tag for that. Also, maybe you grab from the skills listing Python. Maybe you grab from the job description the word Python. You can grab major types of things as well. If you have previously stored some weights from a machine learning system, the actual real-time scoring is as simple as this very straightforward SQL query. It's just grouping by listing ID, finding the tags that overlap, adding up the weights, and returning the top 1,000 rankings. And so this is something that can be done in, 100 milliseconds or something like that, and is a good start for generating the recommendations. The Finery Ranker, I don't want to go into too much detail on it. There are lots of ways to do this. Tony earlier kind of mentioned some of them. There's this general category of algorithms called learning to rank. You can look at individual sort of items. You can look at whether pairs are ordered correctly. You can try and figure out come up with a loss metric for the ranking of the entire list. In our case, we're just doing right now something really simple, which is estimating the probability of applying given that you've seen the listing. The tricky part here, if you happen to be a data scientist, you're thinking about this, okay, so historically users have maybe applied to a half a dozen jobs or something like that if they're relatively active users, but they could have seen 100,000, right? So this is a wildly imbalanced problem. So a lot of the kind of tricks to getting this to work are trying to find a plausible set of jobs that they could have applied to but didn't, but not so many that you have this wildly imbalanced data set. Once you've done that, then you can apply a relatively straightforward off-the-shelf machine learning algorithm. In our case, we used boosted trees. Tree models are kind of nice just because they tend to like a linear model, like a regression model or something, tends to like to add things together. But when trying to do this matching problem, you really kind of want a more nonlinear types of thing. Just to give an example of a way that sort of the tag matching thing that I used on the rough ranker doesn't work. So think about a job for an entry-level salesperson, right? So you're looking for a 21-year-old who's never had a sales job before. What in their resume says that you're going to want a sales job and that you're going to be good at sales if you've never done it before? It's not like not like a data scientist job, but let's say a mechanical engineer. If your major is mechanical engineering, probably your job title has the words mechanical engineering in it. Sales is not like that at all. And probably the thing that is a really good cue that you might be interested in a sales job is that you are not an engineer. I, for example, would be terrible at sales. And so this type of thing is much easier for a nonlinear, like a tree model, to pick up. Okay, so that's most of what I want to talk about at the algorithmic level. What about the implementation level and the code? We intentionally made this as boring as possible. Again, with a really small team, you don't have a lot of sort of support to manage a custom set of tools. It's hard enough to deal with the microservice and everything else. So the stack that we have in production now, so start out with Python. The main application, WayUp.com, is a Python app. And so this is very handy because now I can go to my colleagues, the software engineers, and be like, help me with this problem, look at this pull request. Even if you don't understand the data science piece, you can at least understand the language. Also there's really good tools for machine learning types of things in Python. For the web layer, the web API, we use Flask. This was actually a change from what the main application uses, which is Django. Django is a very heavyweight system for building large websites. That was wildly overkill, and using a very small system made a lot more sense here, much easier, much less for me to learn. In terms of data stores and data technologies, off-the-shelf things like SQLite, off-the-shelf ways of moving data around like S3. For the machine learning components, scikit-learn, linear models, XGBoost, Spacey, which is a relatively new but quite extensively used natural language processing system. All of these used as straightforwardly as possible to do things like tag extraction, weight identification, the Finery Ranker, and so forth. In terms of the actual deployment, again, using everything totally standard with the rest of the application framework, building Docker images, doing continuous integration and testing, dev staging and production environments. All the logging and monitoring looks just like everything else that the rest of the application team is building. And again, with a really small team, don't have the resources to do anything totally new and different. So that was the real-time piece. I also want to talk a little bit about kind of everything else that goes around. So, in data science, 90% of the work is massaging the data and feature engineering. In production machine learning engineering, actually only 1% is the fun stuff. 9% is the data, and 90% is everything else that you build to actually get the thing into production. And so one of the things to get right is what happens when. So I told you about the real-time thing, where in real time you're generating these tags for users and doing other types of processing, the boosting, the query, the re-ranking with the fancy algorithm. On the manual side, so maybe once every 3 months, that kind of thing, you probably want to rebuild the ranking algorithm, rebuild everything. So the world doesn't change, job listings don't change that often. You don't really need to change things too much unless you're changing the algorithm itself. So basically rebuilding everything from scratch probably should do every once in a while, and whenever you're able to add heuristics, add new features, we have a process for doing that where you can sort of test and make sure that everything is working well, but it's important to have the data scientist in the loop during that part of the process. This said, there are things you have to do pretty close to real time, so new jobs come in all the time, and you'd really like to rank them or recommend them whenever they're available. So twice daily, we have a system that pulls whatever listings are now active from a database, generates tags and weights for those using pre-learned weights, and saves some artifacts for the real-time system to pick up. And in terms of the rough ranker, which I described before, the component of the batch processing task looks roughly like this. So kind of orchestrated by Airflow. We have this ETL process, which is going on to support the data warehouse and other things, but also data products like this. There's a listing tag generator that pulls the tag weights out of an S3 artifact, which had been previously stored, and then builds a SQLite database for real-time scoring that gets dropped onto S3. So whenever a real-time scoring system grabs that SQLite database, it has an up-to-date set of job listings that it can recommend. Okay? So on top of that, there's all this other stuff that you want to build. I really want to talk about this pattern because I think it's really important, and I've done this several times and it has been unbelievably valuable. So when building a predictive model or a recommendation system, sure, one of the ways that you can see whether it's working is you can turn it on and look at the main web app screen and see if you get some recommendations that look pretty good. But that's not enough. It makes a huge difference if you can build APIs to allow you, as a data scientist, as a machine learning engineer, to build a system that gives you an alternative debugging interactive system for looking at, in this case, at looking at recommendations. So I built an app in Shiny, the R-based web tool system framework that can hit the API, the main API from the recommender service, either in production or in staging or on a local machine, can do the main scoring task, so give me the job for this particular user, but it can also do other things. So like, tell me about this job. Just give me the tags back, not the recommendations. Tell me about yourself. What version are you? When were you last updated? All that kind of thing. Very useful to have access to that. Also, it was useful for the main application to have an API endpoint that goes the other way. So usually the application takes the user data from the database, builds a profile object, and sends it to the recommender service. It's also useful to have an endpoint for me to pull that says, hey, tell me about user 1004, and get that profile information. That gives me a lot of information about an opportunity to kind of play with that request in real time and explore what's going right and what's going wrong. And of course, it's also useful to have access to some sort of database so I can see much more information about a user or a job listing that might not be in either source as contextual information. And this was unbelievably useful for debugging and to make sure that the system was working, to look at staging versions before they're in production and so forth. Highly, highly recommend this pattern. So I mentioned a little bit earlier about A/B testing and metrics and tuning. So obviously, a lot of machine learning is happening offline here, but there are also lots of parameters, all the weights for how to combine things, lots of other types of real-time things that you can play with. And so it's really important to have an A/B testing framework that lets you get to good metrics and good A/B testing. So to kind of walk you through how that works, suppose you are user number 3, and you've clicked the box or the drop-down that says, I'm really interested in part-time jobs right now on the front end of the website. That gets sent to the application. The application at this point does something that is pretty useful. So you're probably familiar with the idea of like a session on a website. That's usually minutes or hours long. We have another type of session that we generate inside the application, which is the context for a particular set of recommendations. So when you do this query, we generate a discovery session, which has some ID. It also has what test bucket you're in. So your user 3 was assigned to test bucket B in this case. Also has any other parameters that were applied to generate the listings. The application then generates the JSON blob, sends it to the recommender service. Recommender sends back a bunch of listings. The application adds that context discovery session ID to that set of listings, send it to the front end. The reason we do this is because we use a lot of sort of JavaScript tracking things, and it's really nice to have that piece of data available all the way through the event tracking process. So that's kind of the back and forth loop. As this is going on, other types of artifacts are being generated. So the database stores these discovery sessions. The logs have things like, user 3 clicked on this listing at a point in time in this particular session at position 1 on the screen. And again, that's amazing data to have. If the user clicks the apply button, we also, as I said earlier, collect a snapshot. So we know what position in a hypothetical set of job recommendations. So this is not storing what they saw, this is storing what they would have seen if they had nothing clicked. So they're kind of default recommendations. And if they had scrolled for 10 minutes. So we're storing lots and lots of these. We get these kind of counterfactual job listings that they could have seen, could have applied to, but didn't. And when you take all these pieces of data and combine them, you can get some really nice, clean data from A/B test things like users in bucket A, 32% of them applied to a listing in their top 10 over a period of time. Maybe it's higher in bucket B, which is great, but you also want to look at other types of metrics. So like what proportion of users applied to a job during this during the time that the test was in effect, and maybe that's a smaller change than the actual improvement in the sort of technical metric of how high in the recommendations were the applied to jobs. Cool, so all these pieces are necessary to get to this data. So to kind of wrap things up with some thoughts, I want to talk a little bit about the impact. So because of the metrics and the A/B tests and everything else that we had built at the beginning before putting the new recommender system into place, we knew the old recommender system was not consistently as good as we wanted it to be. Anecdotal sort of qualitative evidence said the same thing. And we also knew that some of the business metrics, things like applications to customer jobs, needed some love and attention, which is why we decided to build this in the first place. And so when we rolled out the new system over the summer, we used A/B testing along the way to try and evaluate how much this was helping. And got some pretty good results. So when the very first version of this was deployed, we were able to do an A/B test with, it's kind of like not quite a minimum, but pretty not fully fleshed out, not fully tuned version of the system I just described. Compared to that previous system, it led to a 20% increase in applications. So that was great and really compelling. As we did other types of tuning, just to give an example, the addition of the Finery Ranker, which I described, was not in the initial version, just because we wanted to get it out the door. That also led to a further boost. So the sort of the sense of, am I getting recommended things that I actually want to apply to, that increased by 20%. And for customer jobs, that application rate also rose by 5%, which is nothing to sneeze at. We've done a variety of other A/B tests as well and continued to tune the system. Those types of systems also tend to end up with like 5% increases for any given parameter that we're trying to tune. So really important to have the metrics and testing framework, as well as the system itself should be ideally pretty good. So kind of stepping back, we were able to build this recommender system focused on a very specific experience, the experience of that new user who just filled out a profile. So real-time, matching-based rather than collaborative-based or experience-based. a system that incorporates the business goals as well as user goals, sort of combines them in the best way possible. Really happy with the architecture, with the microservice, this two-step system, which scales quite well. Also very happy with the technology choices. Extremely happy with the decision to build testing and metrics first, able to demonstrate value as well as continue to tune. And in terms of ongoing support and maintenance and iterability, the fact that we've got these as a totally separate microservice means that whoever is working on this next at WayUp is going to be able to very quickly make changes, deploy them, and test them quite easily. This said, it's still a fairly complicated system, but I think we made the decision to build this fairly complicated system for good reasons having to do with the business constraints, the site design constraints, the scaling constraints, the resource constraints, and so forth. So thank you. What questions do you have?
It seems like the biggest step when you start iterating along, so you can begin seeing your interacting set. And you said like the existing way was really opted into the engineering. Can you speak more about how that logging is done and you were able to A/B test that tied into the system versus your service approach?
Yeah, so the logging is primarily not done by the microservice. So the main application knows what listings were recommended because it had to look things up and put them on the screen. There were a couple of special pieces that were built, things like that snapshot system. That's like a little trigger that when you apply to a job, it says, okay, when did you apply? Strictly before that point in time, what would the recommendations have been generated? That's kind of like an offline thing. That was built by the engineers. The actual logs from the recommender itself are not as useful, actually, as putting them in context with everything else. Yeah, I mean, still good to have logs on a production system so you can see when it breaks and look at, timing and things like that. But yeah, it's mostly through the main application.
Yes.
Machine learning development state.
Yes.
So when you do not have interaction with the real user, you don't have that much time. That's why you offloaded the machine learning intelligence for database and provide real-time.
Yes.
That's API.
Yes.
So how often do you update the machine learning algorithms and is it being updated? I mean, is it like that process?
Yeah. Right. So the primary learning processes happen offline, run by a data scientist in a sort of manual but workflow design process. And like I said, that doesn't need to happen very often. The part that happens in real time only includes a tiny bit of machine learning, which is like the similarity submodel, which I didn't talk about, because the set of job listings change, you kind of need to do that in real time. But everything else is done offline and batch. And so the only thing that's happening on this sort of twice daily process is just taking the things that you've learned and applying them to the jobs such that you can do the real-time processing very quickly.